Thank you very much for inviting me to come and talk at your meetup. I'm going to talk to you a bit about EEG, and there's two messages I wanted to communicate as part of the talk. The first is that EEG is becoming useful for cognitive tasks. Now, EEG is quite an old technology. We've been doing EEG for 100 years now. To a certain extent, for a while, EEG was becoming eclipsed by other neuroimaging techniques like fMRI, etc. To a certain extent, MEG. But more recently, or what I'm trying to suggest to you is that because of improvements in data analysis and clever techniques for using EEG, it's becoming, again, useful, but now maybe useful for more high-level cognitive tasks that it hadn't been applied for before. So I'm going to talk a little bit about EEG and cognitive tasks by looking at a specific example of interest to me, which is in neurolinguistics. And one of the other things I wanted to sort of advertise was Bayesian techniques for analyzing EEG data, and maybe also making a general plea for Bayesian approaches. So that's again just what I'm saying. This is EEG. You put electrodes on the brain. You're looking for changes in the voltage in the brain. It's quite complicated. You might wonder, why would there be voltages in the brain? And of course, the answer to that is that the neuronal signal that occurs in the brain, it involves the movement of ions, that creates currents and voltage differences. Those are what we detect. Now, you might also then think, well, why is it that they don't all cancel out? Why is there a net voltage that to be detected? And the answer there is that what we're actually measuring, or our ability to measure EEG is based on, the fact that there is an overall orientation to neurons. So although most of the field does cancel out, there's a little bit left over. I think it's ironic to think about where EEG came from. I don't know if you all know this story, but EEG was first developed by Hans Berger, as I said, over 100 years ago. Hans Berger developed EEG because he'd had an accident. He spent a year in the army, or sometime in the army. I'm not sure if it was precisely a year, but he interrupted his college studies back in 1892 to spend some time in the army. He was riding a horse, as you did in the army back there. He fell off his horse. He was almost crushed by a cart carrying a cannon. He was unharmed, but shaken. And then later on, he discovered that around the time that he fell off his horse, his sister, who he was quite close to, had become worried about him. And in fact, was so worried that she encouraged their father to send a telegraph to Hans Berger to see if he was okay. And Hans Berger was fascinated by this. I mean, it's presumably just a coincidence, but he thought that this was evidence of some sort of telepathy. And so he tried to actually, because he was the scientific by nature, he tried to find a scientific basis for that. And he thought that it must be that the voltages in the brain were strong enough that one brain could influence another. And so he set about recording voltages from the brain. As I said, he was able to measure them. But this is the irony, the idea that the voltages in the brain are strong enough for telepathy across kilometers so that his sister could realize that he'd had an accident. Well, I mean, that's completely wrong. The voltage signals in the brain are extremely weak. They're extremely noisy. They're both noisy because, as I said, the whole fact that we can detect brain function-related voltages from the brain is surprising because they sort of cancel out. The brain is bathed in this fluid, this salty fluid that's more or less the worst possible thing for the brain to be bathed in if what you're trying to do is record the voltages from the brain. And then there's other problems, which is if you're trying to do a cognitive task, people are, you put participants in an EEG cap or patients in an EEG cap, they're always thinking about something else. When will I be able to stop sitting in this dark room wearing an EEG cap, I think is what they're mostly thinking, and often they even fall asleep. So, there's a lot of difficulty trying to detect stuff using EEG. And so, as I said, people have used EEG for sleep studies. In fact, this whole structure of sleep was discovered using EEG. It's a remarkable thing that nobody had ever noticed before EEG, that there are different stages to sleep. So the existence of a REM period when your eyes move behind your closed lids people only really noticed that or thought it was significant after we started recording sleep EEG. EEG is used traditionally in the diagnosis of epilepsy and was used for localizing the eleptogenic centers, the places where epileptic fits are starting in the brain. So, there is a long history of EEG for diagnostics, but only for these very, very basic tasks. And as I said, what I'm trying to suggest is that it's now becoming possible to use EEG for more high-level tasks, and that might mean that EEG becomes a relevant diagnostic tool for psychiatric disorders. But my own interest, as I said, is in computational neurolinguistics. I'm interested in how the brain processes speech. And the reason I'm interested in that, well, for a start, it is kind of amazing. I mean, sentences like this. I mean, I'm trying to fit in with the linguists I now have to hang out with a bit. And they always love producing sentences like this that illustrate to you how complicated neurolinguistic processing is. And they choose sentences that are slightly hard to read, that make you aware of all the complicated things that are going on, how you have to take the words and work out what the words mean, but also work out what the words mean relative to their lexical or syntactical case. So you have to work out, what the axe is doing here. It's the farmer who has the axe and not the cow. So, it is very complicated what we do with language. What we do with language, of course, is part of what makes us human. And these days, neurolinguistics is a cool field to work in because, as I'll allude to again, machines are able to perform linguistic tasks that they weren't able to perform before. So it was the case until recently that the only thing that we knew of that could talk was us, but now machines can do it too. And my interest in neurolinguistics came about because I went to a talk some years ago where I learned that what neurolinguists believe about language is really quite strange. And this all comes about because of Noam Chomsky. So Noam Chomsky, who's still alive and in his 90s now, as quite a young man, so as much as 70 years ago, revolutionized linguistics by, he did lots of things, but before that, linguists were mostly interested in saving dying languages, etc. He proposed this idea that languages have a universal structure. And this is how he put it: in their essential properties and even down to fine details, languages are cast in the same mold. The Martian scientists might reliably conclude that there's a single human language with differences only at the margin. So when I first heard this, I thought it was clearly nonsense. One of the reasons I thought it was nonsense is that the other language I know, which is the Irish language, called Gaeilge in Irish, is so different from English. Just as a quick example, in Irish, when you want to say that you have something, you don't have a verb to have. In fact, you use a preposition. So Irish has these compound prepositions. Agam means at me. And to say that I have a newspaper, you say that the newspaper is at me. So it struck me that this idea seemed false. The idea that languages had a universal structure that was only tweaked a small bit from language to language. That seemed like a crazy idea. Nonetheless, there's lots of evidence for it, and the evidence starts with things like how quickly children learn languages. Here's a sort of classic bit of evidence. The Kellogg's, who are two neurolinguists in America, raised their child Donald with a chimpanzee. So the idea was that when Donald was born, they went to the zoo, as you do, and asked for a chimpanzee. They were given a chimpanzee at roughly the same age as their child. They raised them together. They tried as much as possible to treat them the same. At first, the chimpanzee and the boy were doing, pretty much the same developmentally. The chimpanzee actually learned some things like getting dressed itself slightly quicker than Donald did. But then somewhere around the age of 2, Donald learned to talk and Gua, the chimpanzee, didn't. And then, unfortunately, Donald started Gua didn't learn to speak, but Donald did start throwing his feces at his parents. And so they sent the chimp back to the zoo and the experiment stopped. But what we can see there is that there's something in the human brain that allows humans to do language. So it's not just that your general cognitive ability allows you to do language. The brain has some structures that make it easy for the human brain to learn language, and the chimpanzee doesn't have that structure, and so it can't learn language. You might say, well, how can maybe the chimpanzee couldn't learn how to talk, and there was other experiments done in similar circumstances, but with sign language rather than spoken language. So that's evidence for the idea that there is a universal grammar, that languages have a universal structure, and that structure is present in the brain. Against, as I alluded to before, is this idea that chatbots are able to transformers are able to learn to speak. They're able to produce language, and they do it without computer scientists supplying them with some sort of universal grammar. Just like the chimp, a transformer doesn't start off with a knowledge of the universal grammar. It just looks at lots and lots of examples. I mean, quite famously, computer scientists believe that trying to include the insights that linguists had about language into machine learning held back the development of language-capable machines for a long time, and that the slogan was always, if you want to improve your language machine, you should fire your linguists. These are two sides of the thing, and the question is which is right. And so I as I said, when I became interested in this topic because I heard about this, but I heard about it in the context of a talk about what I regard as an amazing experiment. So the amazing experiment went like this. So these people, Ding and Peeble being the most famous, took participants, they put an EEG cap on them, and they tried to detect the grammatical processing that these people might do. Now, as I mentioned, EEG signals are really really difficult, really noisy. This is a cognitive task. We're trying to detect the brain doing something with language, parsing language, bundling together words in a way that allows the grammatical structure of the sentences to be extracted. That's much too noisy for most approaches to looking at these data. But what these people did was very clever. They took this apparently sort of random string of words until you start reading it, and they played them at a very precise speed. So they played it, so basically, I'm going to say every 250 milliseconds, although the precise timing was slightly different. They played each word for exactly 250 milliseconds. And in fact, this stream of words contains phrases and sentences. Fat rat sensed fear, kind words warm hearts, young child closed doors, wood shelf holds cans, long fight caused hate, thin thread hang plates, etc. So each of those four-word sentences, well, each four words is a sentence, and within each sentence there is two phrases: fat rat, sensed fear, or new plans give hope. This is a noun phrase. The subject noun gets bundled with its adjective to give a noun phrase. The verb gets bundled with its object to give a verb phrase. And so you have this structure, and these different structures are appearing, sorry, I'm saying the wrong side. These different structures are appearing at different frequencies. So there's a purely stimulus-driven frequency, which is 4 hertz, because each syllable is 250 milliseconds long. But then there are two other frequencies, one associated with the phrases and one associated with the sentences. And so in looking at the EEG now, you don't have to look at the EEG response generally. You can bandpass and look specifically at the EEG, or take an interest specifically at the EEG response at these syllables and do more advanced processing. So here again is the same idea. We have, as I said, it's the precise length of the phrases isn't 250 milliseconds. It's just easier to talk about it like that. You have this level here, which is the purely stimulus-driven signal. You've got a phrase-driven signal, and you've got a sentence-driven signal. And this is what they saw. So if the words were just random, you see a peak here. So this is some measure of the response. In fact, it's the so-called intertrial phase coherence. It's some measure of the EEG response. This experiment is done with MEG because these people have lots of money. But you're looking at the response in the brain. I'll show you EEG results in a minute. We're looking at the response in the brain at different frequencies. And we're looking at some measure of that response, which, because the signals are so complicated, has to be a sort of a derived signal. And we see that when the words are just random, we see a response at the syllable rate. So this is to the words themselves. But when the words have a structure, we see a response at the phrase and the sentence rate. And so what we're seeing is that the brain is doing something when it hears a whole phrase. And so we can see directly dynamics in the brain that is parsing the sentences and doing the sort of dynamics we would expect if, against certainly my intuition, the brain has some structure specifically around classical grammatical manipulation. So the brain in this picture isn't doing the sort of statistical reasoning that a large language model would do. The brain is applying the rules of grammar. And so, we are able to see in the signal something that's not in the actual sort of stimulus, unless the brain is performing a cognitive task. In other words, these peaks are related to a cognitive task. Now, just to sort of say in passing, this is about linguistics. We're interested in linguistics. We've put the other structures in, like the phrase structures, or these people have put the phrase structures in because they're interested in neurolinguistics. But you could imagine other things that could happen. So there are people who are trying to do this from memory. They're showing pictures, and every fourth picture is something that the patient or participant has seen before. The other pictures are things that they haven't, or every second picture rather is something the patient has seen before. Every other picture is something they haven't. And so if there is this peak at the first harmonic of the stimulus presentation, that means they're remembering. If there isn't, they're not. And so you can imagine that gives it makes this sort of frequency tag paradigm an assay for memory. Or you could have happy and sad faces, etc., and use it as an assay for emotional state. Anyway, to go back to the neurolinguistic story, Stephen Frank, very skeptical about this, Chomskyan view of language, pointed out that in fact you could explain all of this just with statistics. You could say that in new plans bring hope. Bring and hope are words that often go together, as are new and plans. It's got nothing to do with the brain recognizing that one's a verb phrase and one's a noun phrase. It's just the brain doing stats. And so he did some, model of this and showed that he got a very similar result to Ding and people and so on, just based on word frequencies. And so we tried to check this. So we did another experiment where we did something very similar. We just looked at phrases, noun phrases, old rat, sad man, ill wife, etc. But we very carefully controlled for all the statistics. So we looked at corpuses, we extracted the statistics, we made the stimulus so that the statistics are the same for this case, which is the adjective noun case, and we also looked at an adjective verb case, which is ungrammatical, but we made sure the adjectives and the verbs were still ones that co-occurred as often as, so for example, ill wife does. So here's the adjective verb case: rough give, ill tell, thin chew. We made sure that thin and chew are as likely to be beside each other as ill and wife, but here we have some sort of grammar. Here we don't, and we did the EEG experiment, and we still see the peak. And so. So we saw, contrary to our expectations, frankly, that this Chomskyan linguistic account of how the brain deals with language seems accurate. So that's one thing I want to say from my point of view as a linguist. But the second is we are quite clearly in an EEG experiment seeing a cognitive phenomena, and I think that's promising for other diagnostic approaches to EEG. This is just based on where the electrodes were, where we're seeing activity. We're seeing activity. So this is the adjective noun case versus the adjective verb case. We're seeing activity over the temporal lobe, which is where you do your hearing, and we're seeing activity somewhere in the visual cortex as well, which is something to do with people imagining things happening if they kind of make sense. But we had all sorts of other conditions. This was there's different types of phrases and different types of nonsense basically. And when we look at the skull caps, we see activity for some of them as well. And what I wanted to get into now, very briefly, is the idea that although we were quite happy to see this, I did want to sort of make a warning, which is very often for these sort of data where you don't have very many participants, running an EEG experiment for linguistics, it's quite a lot of work. You tend, I should emphasize that, of course, EEG is so much cheaper than MEG or fMRI or anything like that. But even so, we had 20 participants in our experiment. You have a lot of electrodes. You have, in our case, we're using 32, but you might have 64, etc. The stats becomes quite difficult. And so when you start to look at pictures like this, where you see activity here in this electrode, you might start to think that there's something there, but proving it's there would be very hard just because you have all sorts of multiple comparison problems. And indeed, sort of there's a moral problem, which I don't want to talk too much about with the sort of computational approach, which is that to work out the thing that we're measuring, the intertrial phase coherence, that's the thing that's measured here, which is really the way in which the response track is tracking the signal. You have to do quite a bit of calculation. You do Fourier analysis knowledge, which is fine. But what you also do is you take all the trials, bundle them together for each participant. So it's like the thing that goes with a participant is already a kind of an average, and then you compare that across the participants. And that's a bit of a statistical sin. You're not looking at items, you're looking at participants and then trying to do statistical analysis. And so the way out of that is to do Bayesian analysis. And so I just wanted to say a few words about that. But first of all, I wanted to make a general plea for Bayesian analysis, which is that science seems to have, certainly cognitive science and psychology, etc., seems to have got itself in a bit of a bind as far as statistics is concerned, because very often the data has a very funny shape. You've got lots of data about a small number of participants. And that often ends up in a situation where either it's very hard to prove what you think is true, or you think things are true that are not. And so psychology is in the midst of this replication crisis, which the poster child for the replication crisis, of course, is this experiment here about smiling. So it's a very clever experiment, a very classic experiment, where you try to prove that when you're smiling, you're happier. And so you try to make people smile in a way that isn't related to their actual mood. And so what they did was they got people to hold a pen in their mouths. Now, it's not so clear here, but the idea is they either told the people to hold the pen in their lips, in which case they ended up with a frowny face, or between their teeth, in which case they ended up with a smiley face. And they then showed them cartoons and asked them how funny the cartoons were. And because this experiment was done when? In the 80s, I suppose? It was before funny cartoons were invented. So they were showing them Gary Larson cartoons. And I remember thinking Gary Larson cartoons were funny, but I really don't see why this is funny. But maybe that's because I don't smile enough. But it turned out anyway that the people are smiling only because they're holding a pen between their teeth, found this funnier than the people who weren't. And so this, of course, then forms, it's a very classic experiment. It forms the center of a great many motivational speeches. You know, people on the motivational speech search who tell about this, give this and say, if you fake it, it becomes true. Now, I do believe if you fake it, it becomes true, but not specifically in this case, because this experiment has completely failed to replicate. And I think the problem there is, in psychology, you know, the idea that the inferential basis for science is around proving things is completely wrong. Science is very bad at proving things. It was never about proving things. It was about describing things. And so the advantage of Bayesian analysis is it is about describing things. So I just want to sort of mention in passing that it is, I think, morally the right thing to do to move science to an inferential framework that involves description through Bayesian analysis rather than proof using significance testing. So in a Bayesian description, you have some data X, you have a model theta, which is, given the model, theta are the parameters of the model, given the model, how likely is the data? That's what a model is. It's a way of going from your idea to the data. And what you want to do is to know how right your idea is. And so that's working out the probability the other way. How likely is your model given the data? And you can do the inversion, of course, using Bayes' rule. If you have some data, you have some priors for the model, you can work out how likely the model is. And that's a description then of how good your model is. That's how we should do science. Bayes has many advantages. It's, as I was trying to outline, it's honest and modest. It really is doing what we can do, which is to say how good our description is. It's also actually very efficient. It's very good at using your data in an efficient way. And before, it was always really hard to calculate this, p theta given x. It was hard to do Bayesian analysis. That's completely changed. And this is an unsung victory of modern science because we've been distracted by machine learning and deep learning. Nobody's noticed that actually Bayesian analysis has sorted out how to calculate posteriors using a technique called Hamiltonian hybrid Monte Carlo, an advert for anybody who's interested. If we use these on our data, we get the same results. In fact, they're slightly cleaner. When we look at the skull caps, those results that looked tempting have completely gone away, so they weren't actual results. The results that were true are still there. That's just a comparison to show that. And in fact, this is a comparison of how efficient the two approaches are. So I'm not, of course, detailing the Bayesian approach, but you can reframe all of this in a Bayesian way. And what this is telling us is this is imagining a sort of simulated experiment where we only had a smaller number of participants. So to get the result, what we'd call a significant result before, we would have needed at least 11 of the 16 participants. To achieve the same sort of inferential power, we would only need 9 in the case of the Bayesian analysis. And this is sort of generally true, that a Bayesian approach to data is much more efficient. And so that's sort of one story. I think there are more stories about how we are getting better at using EEG. You can use machine learning powered dimensional reduction. That seems very powerful. It allows you to draw conclusions. We can actually do some mixture of machine learning and dynamical modeling. But generally speaking, what I want to say is that although EEG is an old technology, it's a very cheap and robust one. It was always good for things like epilepsy and sleep, but I think in the future it will become good for cognitive tasks and maybe good for diagnosis in psychiatry. Thank you. Sorry.
Thank you so much, Dr. Houghton. Now we have time for a brief Q&A session. So please, if any of you have any questions, raise your hand and my colleague will pass the microphone to you.
Peter Barnes, returning to your chimpanzee child, I understand that chimpanzees have been taught to sign in some experiments, and I wonder whether you also conducted any experiments that take in signing.
Well, I'm not in a position to work with chimpanzees, I'm afraid, but the signing experiments are very controversial. I mean, it's an unfortunate thing that those experiments were very inconclusive, and the danger with animal experiments is the kind of clever hands effect. You know, the idea that animals are actually very good at doing what we want them to. And so there were two substantial chimpanzee experiments, but both of them only involved one chimpanzee. The first one, the experimenters around that chimpanzee believed that the chimpanzee was communicating with them quite effectively. In the second experiment, the experimenters had thought that and then changed their minds and decided, and their belief was that the chimpanzee wasn't signing to communicate. It was signing because it was trying to make them happy. The sort of conclusive statement is that the chimpanzees didn't teach their children to sign. They didn't sign with each other. The other famous example of an animal that some people believe, learned to talk was the grey parrot, Alex the grey parrot. That was a very tragic thing in the sense that the parrot died, and Irene Pepperberg doesn't seem to have been able to train another parrot to talk. It seems to me possible that parrots can talk. I mean, obviously they can talk this, and they can imitate our language, but it's possible that they can only do that because they actually talk to each other as well. And that wouldn't be completely surprising. They're quite social animals. Parrots, as you probably know, are extraordinarily smart. The bird brain is much more efficient than ours. There are these experiments done or these studies done where you count the number of neurons or pyramidal neurons or forebrain neurons or cortical neurons in the brain as a function of the size of the brain. And of course, for most animals, the bigger the brain, the more cortical neurons. And you have mammals doing that, you have primates doing that, we're up here. And so although our brain is smaller than that of a sperm whale, we still have more neurons. And of course, birds, it's even higher. If a parrot was as big as us, it would be 5 times as smart as us. I mean, a crow is as smart as a cat.
Deaf people who have sign language.
Yeah.
Do they have they been subject to any experiments?
Oh, sorry, I completely misunderstood. I thought you meant to treat. No, I am sorry. That's an interesting question. I don't know about whether they have been subject to EEG experiments. I mean, what is certainly true is that that's one of the other classic pieces of proof for the universal grammar, that the moment deaf people are brought into deaf schools, a language arises spontaneously. And so many of the newest languages are deaf languages. And so that's always taken as evidence that of our ability to form languages out of words. When deaf people are in the home, they often have what they call a home sign. So it's a deaf person talking to hearing people. The hearing people don't take the deaf person's sign seriously as a language because they don't, the deaf person's signs haven't had a chance to develop into a language. And so they have a series of signs for very stereotypical situations, a bit like animal utterances, a sign for table or a sign for salt. Then when deaf people are brought together in a deaf school, very quickly those home signs develop into a language. It's kind of one of those amazing things that demonstrate, what Steven Pinker calls the language instinct. So, I mean, I think that is a very strong evidence for a universal grammar, or at least for a language instinct. But the idea that a language instinct has to mean a universal grammar, maybe that's naive. Maybe it's that the brain is trained to learn to speak it, and maybe the grammar isn't universal, because it certainly has been very hard to find universal aspects of grammar, much as people have tried. And of course, the fact that machines can learn to speak without a universal grammar doesn't mean that there isn't a universal grammar, because ChatGPT-4 learned on a huge amount of data, much more than 1,000 times more than a baby ever hears. And ChatGPT-4 is given it's given the data in a very prepared way, whereas children, we think of ourselves as teaching children to speak, but of course we don't. There are lots of cultures where children aren't taught to speak and they speak just as fast.
So if EEG has been around for about 100 years or so, it raises an interesting question for me about data reuse. Do you think that there's significant amounts of EEG data in a repository where
no.
if you could post-analyze it with newer analytical techniques, it would render something useful or no?
I had an EEG when I was 12 because I had childhood migraine. And, these days, if I present with childhood migraine, they would, worry that there was something wrong with my brain and do a structural MRI. But at the time they did an EEG, they showed me flashing lights. And I remember as clear as day that the set of biros moving backwards and forwards across, all of them on little hands, arms moving. I have a colleague who was trying to get me to post-analyze some of their EEG data from experiments they'd done in the early 90s, and they gave me their tapes of the magnetic tape flaking off. I think we've only really started thinking about data reuse recently. I think, in the history of science, there's a large amounts of data that nobody ever thought that would ever be reused, and so was not stored in a way that's useful. So it's a frustration to me because I have students who are, we're doing EEG. We do all sorts of different approaches to EEG data analysis. A lot of people now put their EEG data on the web, but even then it can be quite hard to work out what the metadata is, work out how to align the stimulus with the recordings, etc. I think it's something we're getting better at now, but I don't think it was something that people ever did very well.
But you have an interesting point here. You're not trying to claim, I don't think, that it's as good as MRI data with glucose and donut and have all sorts of hybrid lead stuff. It's a cheap form of measurement that might just produce good enough data for certain use cases.
Right. So, I think there's two answers to that. One is for linguistics, my particular interest. fMRI is not so useful because of the time resolution. So EEG data has much better time resolution. Now, there's better data that you can have, such as ECOG data. So somebody who's having an epilepsy workup, as you know, they often put electrodes on the brain itself, and then the data is much better. But for neurolinguistics, EEG is better than fMRI because fMRI is too slow. The time resolution of fMRI is of the order of 1 to 2 seconds. Language happens at 4 hertz, 5 hertz. But separately, I'm suggesting that EEG data might have other medical applications, in which case the sell would be that this is something that can happen in a doctor's clinic, and then you can screen people, and some of them might end up with a full workup, which is much more expensive. But this is the sort of also a tool, because I don't know your experience of diagnosing psychiatric disorders. It's something that I do have an interest in. I've worked a bit on anxiety, depression, etc. And the diagnostic criterion are so unscientific in some ways. Somebody comes in and they go through the questionnaire from DSM-4 or whatever, and and then prescribe them. And so it'd be nice to have other more quantitative diagnostic criteria, and maybe EEG would form part of that process.
So I actually work with AI and neuroscience, and some of the stuff you touched on, specifically about grammar. I haven't seen much in grammar actually, but in terms of just speech reconstruction, I don't know if you know of the paper, I don't remember where it was published, but it was fMRI speech reconstruction using, I think, 16 hours of
that's
data.
insane.
Yeah. But I was thinking as well.
We can't do that.
Which one? Sorry.
I said we can't do that.
Oh yeah. No, but I saw, because I think my research team, were planning on doing something based on another study, which was EEG speech reconstruction, but simply just the vocabulary, a single word. And I think the accuracy was chance accuracy would be obviously as many words 1 over, so it's very low. But the accuracy it produced was 60% for predicting a specific word just from the brain signal. So I don't know. Obviously, you're talking about grammar and different things and structure, but what do you think in terms of using the entire brain, or which brains we should localize, or maybe the potential of AI for all the things you're working on?
We're very interested in one of the main things we're trying to do is to try and understand the similarities or dissimilarities between how machines treat language and how the brain treats language, whether the representations are the same or different. So, that's something that we're very interested in. For example, do work on using representations inside a transformer to predict EEG, which is, I guess, the opposite of what you're trying to say. I think there's huge potential there. I mean, I think, as I said, I think we're just getting so much better all of a sudden at doing things like that. These word reconstructions, I think, typically they depend on having some reasonable prediction of what the word is anyway. So you're looking at, you're not predicting the word just from the EEG. You're predicting the word you're including the EEG along with context, etc. And I think there's huge potential there. I think that's, I think that's something that is happening at the moment. It seems to be very special cases where people get it to work, but it's a really interesting thing, and I'm super enthusiastic about it because it's one of those things where people are going to do it for technological reasons, but in doing it, they'll be doing things that we're interested in scientifically as well, because we're interested in exactly that. Where is it localized? What is it? What is it that the brain? What is it that's easy to read off? What it is? Is there a difference in the brain between syntax and semantics, or is that something we've imposed on language because the people who first studied language knew Latin? Who knows? But it's I think great days for neurolinguistics.